Hi everyone, in this video we're going to start topic 10.3 and we're going to be talking about intermolecular forces and how they affect things like boiling point. Intermolecular forces affect all phase changes that we had discussed: melting, boiling, freezing point, all of these kinds of things. We're specifically in this class going to focus on boiling point when a liquid transitions to a solid. We're going to be looking at this instead for the majority of these, because this is a complex topic, so we're going to narrow down our focus so that's not too confusing. All right, so we had talked about intermolecular forces, what they are, and intermolecular forces are the attractive forces between two molecules of, they can be different substances, but normally we're looking at the same substances. So we're looking at, say, like a molecule of H2O and a molecule of H2O and how they attract each other in a solution. So what we know is that between different types of molecules, we have different types of intermolecular forces. So between, say, nitrogen gas, which is N2, it looks like this, versus, say, HCl, which is also a gas, it looks like this, versus NH3, which is also normally a gas at room temperature. Sometimes it can be a liquid. It's close to being a gas. Okay. So these are three different chemical structures, and if you'll notice, between these different chemical structures, we have very different boiling points. So these are all quite low, so this is definitely below room temperature, which means they're a gas at room temperature, because they boil before it gets to room temperature. So NH3 normally boils at minus 33 Celsius. So if we had a scale here, let's say we started at 0 Celsius, which is freezing. This is where water freezes, 0 Celsius. And NH3 is going to be here, minus 33.34 Celsius. So that's where NH3 is going to be transitioning from a liquid to a gas. Now if we look, our HCl is at minus 85.05 Celsius, meaning it transitions even earlier than NH3 does. So it has a lower temperature at which it transitions from. And then N2 gas is at minus 195.8. Okay, so it's almost always a gas. You will pretty much never see nitrogen as a liquid unless it's super duper cold. So this is a very unique substance that you normally don't see as a liquid. There's a reason that these things are in this specific order. There's a reason why nitrogen boils at a really low temperature and our ammonia gas, the NH3, boils at a higher temperature, even though it's much lower than water. This is because of intermolecular forces. Remember, when you go from, say, a liquid to a gas, the molecules spread further apart, and we have to break these attractive forces. That requires energy. So if you have a weak force between them, if they're barely stuck together, you can separate them really easily, and it doesn't require much energy, meaning you have a very low boiling point. Whereas if they're stuck relatively tightly together, you have to work, you have to and push it a lot harder to get them apart, which means it requires more energy, which we see with the ammonia gas. Now the reason for this is because of the different types of intermolecular forces. So the nitrogen gas here, this is a nonpolar covalent intramolecular force, which means it has London dispersion forces between two molecules of N2. So if you have these two here, the way that they're attracted to each other is through London dispersion forces. That's their connection, which are really weak. So it doesn't take much energy to separate them, which means we have a really low boiling point. It's easy for them to separate. Whereas HCl is a dipole-dipole attraction here. So between the hydrogen and the chlorine here, we've got a dipole-dipole, which means it does have some more strength and more attraction. So you have to work a little harder to pull them apart, which is why the boiling point is a little bit higher. So we have a higher BP. And then for ammonia gas, we're going to see hydrogen bonding, which is the strongest intermolecular force aside from ionic. So this is that attraction there between the hydrogen and the nitrogen, which means we have a high boiling point in comparison to the other two. Okay, so it's not necessarily high compared to water. Water has a boiling point of 0 degrees, a freezing point of 0 degrees Celsius. It has a boiling point of 100 Celsius, which is very, very different. So this is a high boiling point in comparison to the other two, but not necessarily if you consider all of the other substances that we could be looking at. Okay. So our intermolecular forces affect when certain substances undergo phase changes. They dictate it, they control it. And so we're going to learn these different trends and how to predict them. Okay. So now I'm going to ask you to use what you just learned to rank these boiling points based on their intermolecular forces. Remember that hydrogen bonding is the highest, and then we have dipole-dipole, and we have London dispersion forces. Now, because we just went through a couple of these, I'm going to change them. So let's change this to HF, and we'll change this to HBr. Okay, so give that a try and see which one of these had the highest boiling point and the lowest boiling point based on the intermolecular forces. You may need a Pauling scale to figure out what type of forces these have, and the stronger the intermolecular forces, the higher the boiling point, because the more energy you're going to need to pull them apart. Let's take a look at how to solve this one. So we need to determine what types of different intermolecular forces each of these have. This is hydrogen bonding. These are our only 3 atoms on the periodic table here that can hydrogen bond when they have hydrogen stuck to them. It's our hydrogen bonding. HBr, if you calculate the difference here, you're going to find that it is dipole-dipole. In this one here, there's a difference of 0 between them, so this is London dispersion forces. So what this means is this will have the highest boiling point, and this will have the lowest boiling point, and the other HBr will be in between. So if you look at what temperature these phase changes happen, that's the order they're going to be in. Let's take a look at what happens when you have molecules that have the same intermolecular forces, because we had only talked about differences in intermolecular forces. There are definitely nuances. So if a substance has the same type of intermolecular force, like this one here, this is ethane, and this is propane. These both have London dispersion forces, but they have different boiling points. And the reason for this is because they have different amounts of London dispersion interactions. So for our ethane here, we've only got 2 interactions between these 2 molecules, whereas for our propane, we have 3 because it's just a bigger molecule. So what you'll see here is that when something has the same intermolecular force, we often go by weight. The bigger the molecule, the more attraction there is in between molecules of itself. So the higher the weight, usually the higher the boiling point, because we have more attractive forces. So the more attractive force, the higher the boiling point, and this usually comes by differences in weight if you aren't looking at your different types of intermolecular forces. So in general, you can remember that something with the lowest mass has the weakest force if they have the same type of intermolecular force. Highest mass, strongest force. That's only if it qualifies. Otherwise, the types of intermolecular forces will dictate which one has the higher boiling point. So here's another graph that demonstrates this concept. You can see 3 different substances that have the same type of intermolecular force. There's one silicon. I can't even remember what that one is. This is 10, I believe, SN. So we can see they're all in the same row on the periodic table. They all have hydrogen stuck to them. But what's happening here as it gets heavier and heavier, we're seeing that the boiling point is higher. So 10 is the heaviest, and it's got the highest boiling point here, where silicon is the lightest, and it's got the lower boiling point. And you can see that based on their molecular weight. Okay, so I'm going to ask you to do the same thing. So rank these boiling points of these substances based on their molar mass. So remember that these all of these here have dipole-dipole between them. These are all dipole-dipole forces. So you'll need to go in and look at the molar mass for each of these. Okay, let's take a look at how to solve this. So essentially what's happening here is the heaviest one is going to have the highest boiling point here. So that's going to be this bromine trichloride here. So this would have the highest BP. Oh, I keep doing that. Because it is, it has the highest mass among all three molecules that have the same intermolecular force. The next one would be this one. So this would be our next one. And then this would be the lowest boiling point because it has the lowest mass out of all three of these compounds. And that's how simple it is for these. Let's take a look at another thing that affects boiling point. There's a lot of little nuances. This is another one. So remember that we talked about attraction. So if a molecule can get really close to another molecule of itself, those attractive forces are stronger. Whereas when you space them out here, they're a lot weaker because they aren't as close together. So there's this thing called branching that also mildly affects our boiling point. It's not a huge influence, but it does affect it some. So let's take a look at these two different types of propanol molecules here. So we've got propanol with our OH group on it. These are 3 carbons in an OH group. And then we have propanol with our OH on the second carbon here. Okay. Now keep in mind oxygen is pretty big. It's got a lot of electrons around it. So in comparison to hydrogen, hydrogen only has 1 electron. It's really, really small. Oxygen is going to be a big molecule. So if we put it on the ends of our propanol molecule here, the substance has 1 boiling point. But if we move that oxygen to the center of the propanol molecule, now we have a different boiling point. And the reason for this change is because this branching affects how close the molecules can get to each other. So if we have something that's linear, they can pack pretty easily like this. But as soon as you have it do like this 3D structure, like it's hard for it to kind of get together. And so that affects how close these molecules are. So with the 1 propanol, where the oxygen is on the end, it can line up a lot closer. But as soon as you do this, it's not going to get together as well. And so we see that reflected in our boiling point. You can see here that 1 propanol has a higher boiling point than 2 propanol. Now, it's not a huge difference. It's pretty mild, but it's still there. So this would be like the last thing that would affect your molecules. So the first thing that's the most important when we're determining boiling point is going to be our IMFs. So that is really the most important. And then the next thing would be your molecular mass. And then the next thing after that would be branching. So if the IMFs between the substances that you're looking at the boiling points for are different, that's going to be the factor that determines which one has the higher boiling point, not molecular mass or branching. If the molecular masses of your substance are really different, that's going to affect your boiling point more so than branching. We can see that example if we take a look at, say, like, let's do something really big, like this. 1, 2, 3, 4, 5, 6. So this would be hexanol. So hexanol. This is organic naming. I'm not going to expect that you know this. Okay, and there's a bunch of hydrogens on this thing. Let's take a look at the boiling point for this. The boiling point for 1 hexanol is 157 degrees Celsius. Okay, so that's much more important here than branching. And we can see that reflected in our temperature or boiling temperature. So the molecular mass here is more important because it's much bigger as opposed to branching. Branching affects your boiling point very, very little, whereas the mass affects it more, and intermolecular force differences affect it even more. Okay, so let's apply our knowledge on branching here to this one. The following molecules have similar intermolecular forces and molecular masses. So I'm going to ask you to rank these boiling points based on their chemical structure. Let's discuss the answer to this one. So if we look, each of these molecules actually has the exact same molecular mass because they have the exact same components. We've got 1, 2, 3, 4 carbons, 1, 2, 3, 4 carbons. We've got the same amount of hydrogens and the same amount of chlorines. The only difference is their location. And so what this means is that these are more packed, they're closer together, which means that their IMFs are stronger because they're closer together, which means we have a higher boiling point. Whereas our 2-chloro-2-methylpropane, again, this is organic, not going to expect you to know it. This one has a lower boiling point because the molecules just can't get as close together. So further apart. So just a summary one more time of everything that we learned about what affects your boiling point. First is the strength of your intermolecular forces. This is the most important thing, and it should be considered first. Because that attractive force, we're always talking about the attractive force between molecules. And when you have a stronger attraction here, think about two magnets. You have two really super duper strong magnets. They're going to attract a lot more than if you have two really weak magnets, maybe like a refrigerator magnet. Those are terrible. They like fall off the refrigerator all the time. They're so weak, you know. So that really affects the strength of the attraction. And then we look at the mass. The bigger your magnet, the more it's going to attract because you've just got more attractive forces there in general. So a magnet this small is not going to attract as much as a magnet this big, just because you've got a bigger thing, okay? So that's the mass of your molecule next to be considered. And then the last thing is the shape of the molecule because it's going to kind of prevent each of your molecules from getting close together. So if you can get your molecules really close together, you're going to have much stronger attraction, whereas if the structure prevents you from getting close because it's all sticky or branched or something like that, and it's a weird shape, then it can't do that, and so the attractive forces are less. We had talked last time about what makes water unique, and I feel like you can kind of understand this now that we've gone over our boiling points. So remember this H2, hydrogen sulfide, and water. These structures are exactly the same. They have the same amount of hydrogens, they have the same amount of electrons. The only difference is there's an oxygen in the center of the molecule versus the sulfur. And what that means is that this here is dipole-dipole attraction, and that this is hydrogen bonding. And so what's really unique is that this gas here boils at a much lower temperature than water. Water boils at 100 Celsius. Our hydrogen sulfide boils at minus 60 degrees Celsius. This is a huge difference. And we can see that because of the different types of intermolecular forces here are really making and affecting this attraction between them. So water is really hard to separate, which means you have to put a lot of energy in. You have to heat it quite a lot before it's going to separate and turn into a gas. Whereas a lot of other substances, that's just not the case. I also think that now we have enough information to discuss iodine sublimation. So if you all remember this, I showed you a video where the iodine goes directly from a solid here, solid, and it turns straight into a gas. It goes straight into a gas. There's no liquid phase when you heat it properly. And it crystallizes here, solid. It turns back into a solid because there's like ice up in here, which makes it cold. So it's like hot, here it's hot, and here's cold, okay? So I think now we have enough information to understand why this actually happens, because we talked about boiling points, right? And so what we're seeing here is iodine's a really unique substance because of its intermolecular forces. So iodine is really heavy. Its mass on the periodic table is 126.9. So you add up two of those, it's like 252 grams per mole is its molar mass. It's really heavy. But its intermolecular forces here are nonpolar covalent. Intramolecular forces are nonpolar covalent. So that means that its intermolecular forces are London dispersion forces. So its attraction is really weak, but it's also a really heavy substance. So what happens here is because it has a weak bond, it can separate really easy, but it's also heavy enough that it separates really fast, and it comes together really fast. Because it doesn't take, it's kind of on that cusp of needing enough energy, of too little energy or too much energy. So relatively speaking, it doesn't require very much energy for it to turn into a gas, but it also does require a decent amount of energy. And because it's kind of in between there, it's really heavy, but it also has really weak intermolecular forces. It goes through this phenomenon of sublimation and deposition. So deposition is where it's going directly from a gas to a solid. So I think you can see kind of here the things that are affecting our boiling point and how it's very nuanced. But the couple of things that I want you to remember are the intermolecular forces we talked about, and the molar mass, how heavy something is, and then the branching. So most of the examples I'm going to give you on the exam are going to be very clear-cut because there is a lot of gray area in this topic. But I won't be giving you things that you can't use your knowledge from this class in order to determine the answer. So in the last part of this video, I want you to work some problems so you can really get some practice with this, because it is a little bit more challenging topic, I'm not going to lie. Okay, so I'm going to give you a couple of substances, and I want you to rank these boiling points. You're going to need some information in order to do that. You're going to need to look at the molecular mass of these things, and you're going to need to look at the intermolecular forces. In order to determine your intermolecular forces, you might also need to determine your intramolecular forces until you kind of get quicker at this. Okay, so I'm going to ask you to rank these boiling points. So out of substances, the substance is A here, B, C, and D. Label these from highest boiling point to lowest boiling point. B, P. Okay. All right, let's take a look at how to solve this one. First, we're going to need our molecular masses of everything so that we can determine that, in our intramolecular forces and our intermolecular forces. We've got to answer all of this first before we can really rank our boiling points. So intramolecular forces for this first one, we're going to be seeing nonpolar covalent and polar covalent. I'm going to abbreviate it this way. So the polar covalent is going to be right here, and everything else is going to be nonpolar covalent. So that means our intermolecular forces for this one are dipole-dipole, because we have no hydrogen bonding, and London dispersion forces. So for B, if we look at B, we're going to have nonpolar and polar covalent. And this right here is hydrogen bonding. So we're going to have all three for this one. We're going to have London dispersion forces, dipole-dipole, and hydrogen bonding. So this is hydrogen bonding. This is where the dipole-dipole comes from, the carbon and the oxygen, because that's a significant electronegativity difference. And London dispersion forces is all your carbons and hydrogens with each other. So that's going to follow through for the next ones. We're going to see the same thing here, 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 because they're all pretty similar. Okay, now let's look at the molecular masses. The molecular mass of our first substance is 78.55 grams per mole. The molecular mass of our second substance is 46.08 grams per mole. Our third one is 44.11 grams per mole. And the next one has an extra oxygen added onto it, so it's 60.11 grams per mole. So now let's go and rank these. Remember that the thing that affects our boiling point the most is our intermolecular forces. So that's the first thing we need to look at here. And what you're going to find is that some of these have hydrogen bonding and others don't. So the ones with hydrogen bonding are going to have a higher boiling point. And if we look, all of our molecular masses are about the same. They aren't hugely different. So if you had a molecular mass that would say like 200 grams per mole, that might be significant enough to affect your boiling point and make it go up higher, like our iodine, right? Our iodine has a pretty high boiling point for having London dispersion forces only. So in this case, all of our molecular masses are pretty close together, so it's not going to be a huge factor on our boiling point here. What's going to matter most is our types of intermolecular forces. So let's take a look at what we've got. We have hydrogen bonding here, we've got hydrogen bonding here and here. So that means that A is definitely going to be the lowest because it doesn't have hydrogen bonding. So that's A. Now let's take a look at our other three. So our other three have the same type of intermolecular force, and so we need to look at their molecular mass next. That's the next thing. So our highest molecular mass is going to have our highest boiling point. We can see that here. So D will have the highest boiling point. And then we want to, I apologize, I calculated these masses incorrectly. This one is right. This one should be 60. Sorry, I missed something there. This should be 60.11, and this should be 76.11. Okay, it still doesn't change that D is definitely our highest one. And then we have C, because it's got the next highest mass, and then B. So it would be then C, then B, then A. So that would be the order. A is definitely the lowest because it doesn't have hydrogen bonding, where all of these have hydrogen bonding. And then you can see that their masses get bigger from there. We don't really see the effect of branching so much here because our molecular masses are so different. They're really going to affect stuff the most. You can also see the oxygen, the hydroxide here is in the same position as it is here. It hasn't really changed too much. Okay, let's try another example here so that you can get some more practice. We're going to limit some of these. I'm going to get rid of these. Okay, so I'm going to ask you to look at A through C here and rank which one of these has the highest and lowest boiling point. Remember, you'll probably need a chart like the last one where you look at your molecular mass or molecular weights from the periodic table, your intramolecular forces, so that you can figure out your intermolecular forces, because that's what matters. And then we'll rank these from highest to lowest boiling point. So give us your best shot. Let's take a look at how to solve this one. And so I've gone ahead and gone in and written out the molecular masses from the periodic table for you. This is what you should also have. Let's take a look at our intramolecular forces. For A, we only have carbons and hydrogens, which means we're going to have London dispersion forces. These are only nonpolar covalent, so that's what results from that. The next one, we did this in the last example, we've got nonpolar covalent and polar covalent. So we've got London dispersion forces and dipole-dipole. Okay, and then for the next one, we've got nonpolar and polar covalent. But so that means we have LDF and dipole-dipole. But if you look, one of our dipole-dipole forces is an oxygen and a hydrogen, which means it also hydrogen bonds. So these are actually lined up in order for us. The first one has the lowest boiling point. So A is our lowest. And then it goes to B, and then to C. So our ethanol would have the highest boiling point, whereas hexane has a really low boiling point, which means it's probably, it's a liquid at room temperature, but it evaporates really easy. It has a really strong smell. All of these molecules actually have a pretty strong smell because their boiling points are much lower, say, than water, so they're evaporating or boiling relatively easily at room temperature.